Ideal flow, velocity potential. So in this lesson, we will introduce you another parameter called the velocity potential. Before we learn more about the velocity potential, there are two terms that you need to understand. There are circulation and vorticity. So we go first to the circulation. Circulation for a closed contour in a fluid is defined as the line integral evaluated along the contour of the components of the velocity that is locally tangent to the contour. It is designed as capital gamma, and the equation can be written like this. Gamma equal integral u times dl, which is u here is the component velocity and L here is the distance traveled by the fluid. Circulation can be considered as the amount of force that push along a closed boundary or path. In the other words, circulation is the total push that you get when going along a path such as a circle. Vorticity. Vorticity is shown by Greek symbol zeta. It is defined as circulation per unit area. Vorticity or zeta, or in some textbook it is written as Z, is equal to the value of circulation, which is gamma, divided by the area. Vorticity is the tendency for elements of the fluid to spin. And this is the discussion about circulation and vorticity in Cartesian coordinates. First, you need to draw a diagram like this. You have a rectangular coordinates like this. So this coordinate is actually reflects or showing the molecule that moving in u direction, which is u here, and also the velocity of y direction here. So circulation means that we are now calculating the capable of this element to move in circle. So for example, we need to calculate what is the tendency of the circulation for this molecule to move from here to here to here to here and then come back to its original location. So first, you need to know how to calculate the circulation. The circulation is the multiple of velocity u and the distance traveled by the fluid, mean this distance. So to calculate the total circulation that happened to this molecule, we could calculate as first it moved from here to here. So mean we need to multiply the velocity of u here with the distance of its travel here, which is equal to dx. So from here to here, the circulation value is u times dx. And then from here to here, the velocity is v plus dv. And the distance here is dy. So we add v plus dv dy, and then the molecule is traveled from here to here. At this situation, we know that the velocity u works from left to right. So this is u and this is u plus du. So because the element here now is reversed to the velocity of this one, so we have negative u plus du, and the distance travel of the fluid is remain the same, which is equal to dx. And then molecule travel from here to here, the velocity is now negative, so we write as negative v, and the distance traveled by the molecule here is dy. So we could solve this equation, and we get gamma is equal to dv dy minus du dx. Then, to calculate the vorticity, zeta here, the equation is gamma divided by the area. And the gamma here, dv dy minus du dx, is actually get from this calculation. So we have gamma is dv dy minus du dx, and we need to divide it into the area. So the area here is actually the area for this rectangular shape. So it is satisfied to multiply the value of dx times dy. We solve this equation, we could say that zeta is equal to dv dx minus du dy. So this is the value of vorticity for Cartesian coordinates. Please remember this one. Next, we are discussing about the circulation and vorticity in polar coordinates. You need to draw a diagram like this. So this is the basic diagram for the polar coordinates. It almost similar with the continuity equation. But we assume that the molecule is now travel from here to here, to this point, and then to this point, and finally back to its original location. So the equation to calculate the gamma is we are multiplying the velocity and the distance traveled by the fluid. So for here, from this to this point, the gamma is ur times dr, and then from here to here, the circulation is u theta times du theta times r plus dr, because this is a radius. R is only from until this point, and dr is this length. So to calculate this distance, we need to add r plus dr d theta, and the circulation is u theta plus du theta r plus dr d theta. And then the circulation from here to here is negative ur plus dur dr, and circulation from here to here is u theta in negative u theta r d theta. So we solve this equation, we could get that the circulation for the polar coordinate can be written as u theta dr d theta plus du theta r d theta minus dur dr. And then to calculate the vorticity, zeta here is equal to gamma over the cross-sectional, the gamma over area, and the value of gamma here is calculated previously, and the area here is the area of this shape. So we could simplify the area of this shape is can be simplified as dr, the distance here, times r d theta. So r d theta is this distance, and the r is the value of this one. So it is okay for us to multiply these two values, and we assume it is equal to the area of this element. So we divide these two items, we could get that zeta is equal to u theta over r plus du theta over dr minus dur over r d theta. And this is the vorticity for polar coordinate. Please also remember this equation. And then there is one thing that you need to understand. Not like continuity equation, vorticity is not always equal to 0. So as we know that in continuity, we must prove that the continuity equation is equal to 0. If not equal to 0, it means that there is something wrong in our calculation, and and we need to fix, or we need to make sure that the continuity must equal to 0. However, for vorticity, it is not always equal to 0. Sometimes it can equal to any numbers. So, if zeta or vorticity is equal to 0, we call this flow is irrotational flow. It is not rotate flow. And if zeta is not equal to 0, we call this is as rotational flow. So what is the difference between rotational and rotational flow can be simplified in this diagram. For example, we have a molecule here that moving from left to right. However, the molecule that we could see in a smiley mark here is remain at the same location. So mean this molecule is not rotate on its axis. So mean this flow is irrotational flow region. So here the zeta is equal to 0. So if we see what happened to this flow, it's similar with the flow at the top here. It's flow from left to right. However, if we see the molecule here, the smiley icon here, we could see that the smiley icon is rotate a little bit from point to point. So at this situation, we call this one as rotational flow. So the rotational flow will have zeta not equal to 0.